time for some more maths. I'm going live on Twitch. Hey everyone, this is going to be a bit more about number theory and the fairy series. Or fairy? We're going to go fairy, I think. I've got some more notes from the book. I've got a cup of tea. It's going to go another one of those, just sort of looking at some maths, learning some maths. This is Dual Maths if you're joining for the first time. I'm James. I think I used to be a professional mathematician, but I'm now, I guess, an amateur mathematician. A bit like Ferry, who I've just read in these notes, was a geologist and amateur mathematician. Hello, Maths2222222. Good to see you. And this is a good moment, I think, to shout out to Tattoo _ who followed the channel about 12 days ago and has possibly got a notification just now to say that I've gone live again to do some maths. Hello, Mary. How you doing? You all right? They've done hi everyone, and then that little O salute thing that I learnt about through Twitch. It's educational in so many ways for so many of us. Right, good. Sorry I cancelled last week, by the way. It was one of those ones where I intended to go live, but then on Sunday realised that I was not going to make it home in time to go live at my normal time. So I cancelled last week's stream, which means it's been about 2 weeks since we talked about number theory. I have to admit, I haven't done any of it in between. I haven't done my homework. Pretty bad. What else has been going on? What else have people been up to? Hi, Herb, as well. Good to see you. Yes. Wonder what people have been up to. I've launched the Maths Club again. My sort of project I do at work, where we do a live stream on maths. We've done fundamental theorems, which is a bit of fun with calculus. And we've done a stream about some puzzles where I had this kind of big concept for the episode, that we would do this kind of new problem solving strategy I've never talked about, but as is sometimes the case when I have a big concept in mind, I get bogged down by the details, and we never quite, I don't think we quite stuck the landing on the big concept. But that's on the Oxford Mathematics Plus channel if you want to see an attempt at that. I had the great structure, right? Do a puzzle, do a second puzzle, and then talk about, there's things linked in common between these, that's revealed this kind of way of thinking about puzzles in general. Maybe do a third puzzle. That was my plan. And then, of course, the actual episode is we did one puzzle, we did half of a second puzzle. Halfway, oh no. And then for about 5 minutes I tried to explain what the hell was going on with both. So, you know, I kind of, a chaos of, and that's the professional live stream out of the two that I do. The professional work one, where we run out of time and don't get things done, versus the chill one, where we have all the time in the world and don't need to get anything done. Right. Don't say the answer. Okay, right, yes. No, there is an answer because we didn't finish the second puzzle. There is an open question for people who saw that show. I'm not sure I intended it to be open, but there's an open question for people who saw that show. Is the final answer really 2, or is it more than 2? Good. I think I managed to leave that open for Mary. Okay, fairy series? Or, yeah, I think that's my plan for today. Switch says that I'm live. I've remembered to unmute. Yeah, good. Right, okay. I've immediately directed people over to a different YouTube video, a different content, other live stream. Hello, welcome, bye. Okay, right. Fairy series. So previously on this show, we had a look at this property of, with a function, I suppose, of 2 rational numbers. Do I mean that? I'm not sure if I mean that or not. Let's think. Let's see if I can explain it back to myself. So I've started thinking of it as a function. So if you have the 2 rational numbers a over b and c over d, then you can define this function, I think, that gives you a plus c over b plus d. Now, I'm saying I think a lot because I've realised that I should probably require that these are in lowest terms. Otherwise, you will cheekily, perhaps, make a and b much, much larger, which would affect the number over here. For this to be well defined, I need to say in lowest terms, by which I mean, I suppose, that the highest common factor of a and b should be 1, and the highest common factor of c and d should be 1. And then I think these fractions are kind of uniquely defined as sort of numbers you might have there. Do I need to say they're positive? I think I probably need to say positive. Let's make the denominators positive at least. There's this choice for, I suppose, all of the fractions, but definitely the negative ones. You could say, do you put the minus sign upstairs or downstairs? And then actually that's a choice for the other ones too. Right, great. That notification noise, really sorry if that got broadcast. That was Microsoft Edge trying to give me a year in review for 24. That's right, an internet browser I don't use wants me to look at highlights from a year that finished 3 weeks ago. Thanks. This is why people say you're slow, Edge. Oh, what's right, hang on. What do I want to do? Yeah, I would take suggestions. Math222 wants to do it as some sort of binary commutative operator. I think it is, right? Oh, you're just going to define, instead of putting an F out here, you're going to say, we'll put some sort of like weird time symbol in the middle and say that it's this. Sure, you probably still need to do this in lowest terms thing, so that that's an inherent weakness of this expression on the right, I think. Yeah, there you go. But yes, you're welcome to think of this as an operation that takes two inputs. With this sort of notation is called infix notation, where you have the operator in between. And if you really get down to it, it's a bit weird because the plus, even the plus symbol, nobody should actually change how they do this. This is not a serious opinion, right? But almost all functions with two inputs, we would write like this, I think. If you have a function with two inputs. And addition is like that. So the plus function is kind of a function that takes two inputs and returns a number. But for obvious reasons, you would conveniently write the plus sign in between these. Nobody writes this, with the kind of plus being the name of the function out here. Thinking about functions like this is helpful, I think, if you're interested in computer code, because your computer probably treats all of these the same, but will be handed things with perhaps infix notation. You might also be interested in Polish. What's the name of this notation I'm trying to remember the name of? Polish reverse notation? I'm going to go Polish notation. I've butchered that. It's not quite called Polish notation, is it? The one where you put the symbol at the end. Yeah. Yeah, NPN. Yes, which would be something like 3, 2 plus, where the idea is that the plus takes the previous two things that you had, and that gets you around brackets, which is quite exciting. Some people are big fans of this Polish notation thing, the idea being that plus always refers to the two computed constants, you preceding it, rather than having this kind of ambiguity about having some stuff before and afterwards. I don't know if people seen this. I don't really think it's not really the plan, is it? But this is mildly confusing, because do I mean 5 in the middle here multiplied by 6? I mean, probably not, because you know about BODMAS or PEDMAS or whatever you learned in school. The point of Polish notation is that you don't need that. You can write 3 3 minus 2 2 plus, no, 2 2 times, sorry, 2 2 times plus, and then the operations always apply to the previous two things. So this plus looks backwards and says, well, hang on a minute, how am I going to work out what I'm actually adding? I've got to do some calculation first or something. I think it works. You end up not needing any brackets. If you don't like brackets or BODMAS or those maths challenge Twitter things that go around where they're ambiguous, then an opinion you could have, I'm not saying it's an opinion you should have, an opinion you could have is that we should all use Polish notation. Polish prefix notation. Right, or we should all write brackets absolutely everywhere and have brackets even for things like plus, the plus operation, for which I would then have to write something like times operation of 3, 3, a times operation of 2, 2, and then wrap that in another set of brackets with a plus around there. Wow, brilliant stuff, love it. Charlie in chat does not like BIDMAS. Oh yeah, BIDMAS, BIDMAS. Yeah, you do. I think I learned BODMAS with O for order, which is not order. Yeah. I for indices. The PEDMAS has gone E for exponentiation. I think we're trying to do different names for the same thing, aren't we? Right, that notation sidetrack was sponsored by, brought to you by Maths22222, who wants addition to be written like one of those always on Chill Maths. Addition, open bracket, number comma number. Just to avoid just to avoid confusion, right? So the median is you take the plus of A and C, plus of B and D, and you divide them, or as I now write, division operator of both of those, plus B comma D, close bracket, perfect, no confusion at all. And I get to use that divide sign that I haven't written for about 20 years, so that's nice. Good, that was not commutative, you've got to be careful, they're not always, the order of the things inside matters. Right. Order or indices, there we go, Bodmus, Bidmus. Right, well I hate this almost more than anything else, I'm afraid. I've heard that there's a colon. I saw a very good Twitter poll at one point, which was something like, what was the symbol that you were told about in school that later you never use? There's some sort of universal for division, this sort of universal experience that people in different countries around the world are shown a symbol that's used for dividing that they later never use again. for me, it's a colon with a line through the middle. Maybe for some people it's, yeah. Neutrinos found out how to type it. There we go. For me, it was one of those. I have heard of the colon being used, which I learned for ratios. Also not a big fan of ratios, but I suppose I have to like ratios as much as I like fractions, don't I? Because they are the same thing. Just trying to and what? No, did you use ampersand at some point for something? Hi Neutrino, by the way. Oh, that was Neutrino joining chat. Types divide sign. Nice. Best Twitch community. They can type stuff. It's not all just memes and emoji in this Twitch chat. We get division symbols. Right. What's going on then? Should we do some fairy series stuff? I'm a bit worried that last time I understood stuff, I think. You get all the numbers on a circle, it's nice. But I haven't really got any sense of what this is for. Like the intro at the start talked about this technique of projection to find rational points on the unit circle, and I love that because that solves Pythagorean triples and things like that. And it talked about other challenges. There was a bit with a sphere that we skipped for solving a squared plus b squared plus c squared equals d squared, which I like. So maybe I want to go back to that instead of going on. The introduction also foreshadowed the kind of idea that we would work out which numbers can be written as a squared plus b squared, which we've tried to think about before on this stream, and it hasn't stuck in my head. It's the sort of thing that every year I have another go at trying to learn it, and every year we get there, and then I forget it. Okay. Ampersand is another symbol that you learn and then never use. Until you get seriously into Dungeons Ampersand Dragons. Let's have a chance to use that curly and sign again. Or possibly computer coding, where maybe they're using ampersand for the logical and operator. Anyway. Maybe using vertical bar for or, who knows? Trying to do two conversations at once, that's Twitch, isn't it? Here we go. What am I doing? So I could go through this and look at this other way of laying out the fairy series, but I think I'm more interested in trying to get more of a sense about what this is for. That's a harder challenge than just reading through, right? Because we can go through and read, like, oh, hey, there's some stuff about fairy, and laying them out like this, and you get this series of numbers which are ordered. Are they just in order? Wait, what? Yeah, they look like they're just in order, right? Up and down. Cool. You can put them in order with this and some nice pictures. These are very nice pictures. But maybe I want to find out, how am I going to find out what this is for? Okay, so this is maybe turning into a sort of geometry sort of, I saw some distances in there. Here's another picture with some triangles and some forward circles. What are we doing though? Why do we need to know properties about this sequence? These are nice properties, but why? Oh my goodness, look at that diagram. That's like the sort of thing from a UKMT challenge or something. What's that for? Okay, this is sometimes how I read a maths book, right? To skim through until you see something that looks interesting that you'd like to know more about. What is going on there? Oh, now I'm going to have to find out about forward circles, aren't I? Okay. the key fact is that for any two non-parallel tangent lines to a circle, the distances from the points of tangency to the intersection point of the two tangent lines are equal. Reflecting across the radial line through the intersection point. What are we talking about? Oh, it's across a page turn. I want to know what the diagram's for. It's a good diagram. Looks like a maths challenge kind of diagram. What are we doing? I'd have to know what's going on though, wouldn't I? So I'd have to know what the forward circles are. Okay, maybe I don't care enough, but okay. Memory, something to remember. In there is a semicircle that beautifully goes through the point of intersection of these other circles. So sort of tangency, yeah, it's sort of surprising you can do that, isn't it? If you have two circles, are these just any old circles? Not sure if they have to be or not. But if you have these two outer circles, then what I've spotted is you can draw a semicircle from point of tangency through here. That reminds me, there's a fact about four circles. Can I remember it? No. There's something out there. So this straight line here, it's sort of like having a fourth circle in this picture. There's one in here that goes through here. It's sort of like having a fourth circle that's enormous, which makes me think this is actually a fact. Once I've worked out what the fact is, this is actually a fact about having three circles. Perhaps something is still true when you have three circles, that you can draw a circle through the points of tangency and it will be... it'll meet the outer ones at right angles. That's the fact here, I think. That this circle, semicircle... See, I could just read the text, or I could try and look at the picture and work out what's going on. I've got this vague memory of something about four circles as well. Right, here's what I think is going on. You have two circles sitting on a plane like this. Here are the two circles. I shouldn't say sitting on, it's a 2D picture, right? Two circles that are tangent to the plane and to each other, and it's possible to draw a semicircle through the points of tangency. So the that's the diameter of this new circle that I'm drawing, and then surprise, it goes right through the point of tangency of those two circles. That doesn't sound true in general, does it? Let's find out if it's true or not. Oh, okay, so this is why they're talking about reflecting in this line down to the radius. So these are equal because they're equal tangents, and these two are equal because they're equal tangents, equal size tangents to that circle. Right. Okay, so that is also a radius. Okay, so that's quite a fun fact, I think. Can we use that? Can we Desmos it? Let's Desmos it. So I'm going to try and recreate that diagram in Desmos. Right, what do I need? I need, so we'll have the centre of one of these circles be some movable point AB, and another centre of a circle at CD. But they need to be tangent to each other, so this is going to be a bit of a challenge. Let's draw the first one in first. If you're new to the show, hi, welcome. Sometimes we just do nonsense like this, so I'm trying to draw in the two circles and then a smaller one, but the rule is that they have to be tangent to each other. That's a little bit tricky. That is in itself is a sort of geometry constraint. We can solve some algebra, I think, to work out how large to make this other one. Is it something like the closer it gets, I can work out how... Yeah, so I want it to maybe slide left and right. To slide this left and right, but to calculate D. So C should be a slider, but I'm going to calculate D. Right. It's going to complain. But D should be something based on... D is the height. So D should be something based on... What's this going to be then? The height is going to be something like B. Take away, and then I need to use a little bit of Pythagoras here to work out I'm imagining a triangle. It's annoying that my circle has vanished, but a little bit of Pythagoras here. So that radius was B, and this one will have radius, bother D. Let's quickly write down an equation, I think. Yeah, Yeah, quick doodle in the background. Hang on. So I've got a circle here, and I'm trying to build this. This is D. This is D. The radius. I've picked terrible letters for this, and this horizontal distance is C minus A, I think. So I've got some geometry set up. Where what do I want? I want B minus D squared plus C minus A squared for this right-angled triangle on the top here to be B plus D squared. And great news, lots of B's and D's cancel. Is that just B? That's B minus D, yep. So lots of B squares and D squares cancel. So I'll get something like, on the right, 4BD. C minus A squared is 4BD, so I need to divide by 4B. So D is, a good thing I scribbled that on the side. Is that going to be right, I wonder? C minus A squared, probably not, divided by 4B. And the circle that I want to draw is something like x minus C squared plus y minus D squared equals D. Okay, so that hasn't immediately worked, but I do have a circle that gets larger and smaller. What did I miss? Minus 2BD. B minus D is this height here. B minus D, I want to square that plus C minus A squared. Yeah, Pythagoras. B plus D squared? Yes. Wow. What have I done wrong? C minus A squared over 4B. That should be D. Oh, radius squared for a circle. Radius squared for a circle. There we go. Now we have tangent circles, and I can slide this one left and right. Okay, lovely stuff. I can move this one wherever I want. I can move that one wherever I want. And play with the colours. So it's okay. Blue circle with a blue centre, and a red circle with a red centre. Lovely. And they'll stay tangent. Oh, I'm moving the blue one is a little bit. There's a little bit of asymmetry. Where moving the blue one affects both, and moving the red one doesn't. But I'm happy with that. Okay, that's my general 2 tangent circles. I've just been distracted. If you've just joined in, I've been skimming through a book, looking for something that I'm interested in. I'm interested in this diagram, which I think claims that whenever you have 2 tangent circles that are tangent to the line x equals 0, let's draw that in, y equals 0. Live streaming and doing Desmos at the same time gives me lots of opportunities to make mistakes. Demonstrate that, I suppose. Let's make those nice like that. And that's good. Okay, all tangent. The result is that you can draw in a third circle that goes through all of the points of tangency. Ding, ding, ding. That's not surprising, is it? That's just a circle going through 3 points. Oh, but it's a semicircle, and the centre is on this line, on this purple line somewhere. That's the result, I suppose. What is that? The circumcircle is the point that goes through all 3 points of a triangle. So the circumcircle, yeah, it's saying that's a diameter, which is equivalent to saying that the angle, I'm imagining a triangle, let me draw the triangle. So much of this is imagining what to do next, but also, oh no, how do I label the intersection points? Yeah, there's a right angle hiding in here, right? Loads of right angles. I'm about to draw in a semicircle, which means there's a diameter, which means by Thales' theorem, there's a right angle hiding in there as well. Yes, between the 3 points of tangency. And I've just started drawing this triangle and realised I don't know where to put that point of tangency. It's not there, is it? It's up a bit. Calculation time. This is an old MAT question, I think, to find the intersection. Although in MAT you'd be given some numbers and somebody would have made sure the numbers worked out nicely. So similar triangles. So we come down to this point of tangency. Oh my goodness, b over b times d. This is going to be a hack, but I'm going to use some sort of like vectory stuff. So ab plus that much of the line down. Ooh, from your point of view, it is that way. I want to take that much of it, b much of it, over b plus d. I know its length is b plus d. this line between the centres. A non-lazy thing to do would be something like, there you go, point of tangency. Non-lazy thing to do would be something like find the equation of the line intersected with the circle. I guess I'm using like the vector equation of the line, and I know the proportion of how far along it's supposed to be because I know all the radiuses. Yes. There you go, point of tangency. So the result is that that's always a right angle at that point there, which is, for me at the moment, mildly surprising. That wherever I put these two tangent circles, that angle there, it's a right angle. Said differently, Thales says you can draw a semicircle through those 3 points. Let's put in a semicircle. So what's this going to be? The midpoint is those x coordinates are A and C. I want the midpoint. So let's take A plus C over 2. And the radius is going to be the next question. The centre is on the y equals 0 line. The radius is going to be, it's probably this, isn't it? C minus A squared over 2. You're supposed to square the right hand side. One day I will learn how circles work. R squared on the right hand side. There we go. There's this kind of green circle. Let's put a green polygon in there as well. So one way of looking at this is you get this triangle, and the other way of looking at it is say you get this kind of semicircle where the centre at A over C, the midpoint of the points of tangency with the purple line, is on that point over there somewhere. No, I don't want to move it. Don't let me move it. That's mad. Why would you let me move it? Oh, Desmos, too much power. Whoa, there we go. Good. Okay. Right angle triangles. Interactive Desmos plot. 3 intersecting circles, loads of right angles. Discovered a triangle, put the right angle in. Thales theorem. Are you not entertained? Woo! Here we go. Why is it 2 to the 11 for tea time? Did I set it to 2048? I don't know. That's not a joke. Don't worry, Sensation Black. You're not missing out on a joke. I think it defaulted to 2000, and I edited it to be a power of 2. If you have a funny T joke that we can get, that would be great. So 4 circles. Moving on. Funny T joke that's a number around 2000. I couldn't think of anything. I guess I could make it 1984 since that's the number in your username. I have this control over how many points people switch for the channel point redemption things, which goodness knows. Yeah, so I think there's a fact about 4 circles, which I can't quite remember, but at one point I was interested in the following problem. It's something like, it is different, I now realise, but the problem is something like you've got 3 circles. Oh my goodness, that was awful. They're all tangent to each other. 3 circles that are all tangent to each other. Undo. Don't let them see. There we go. You've got 3 circles that are all tangent to each other, and you want to find out the area, or the radius, I suppose, of a new circle in between that's tangent to all 3 of them. So 3 tangent circles, 3 circles that are tangent, 3 circles that are pairwise tangent to each other externally, 3 circles that are pairwise externally tangent to each other. What's the radius of the circle that's tangent to all 3? There's a fact about that which might come up in this. Because it's like drawing in another circle in here. It's like the inside circle. I know that's 2 circles and a straight line, but the straight line is kind of like an enormous circle. Let me try and find the fact. It's got a name. That won't help us. Let's see if I can find it. Pythagorean gasket? What is it called? No, not that. Apollonian. It's related to Apollonian. Yeah, okay. So here's the Wikipedia page you need to be on. There's an Apollonian gasket, which has got all of these circles in. There it is. There's Descartes' theorem. There you go. The sum of the squares of all 4 bends is half the square of their sum. Nice. So there's some relationship between the radiuses of these circles. Can I have it as an equation? Sometimes known as Soddy circles. Yeah, I had to remember to say externally ones, whatever. There's some relationship between them. That's not quite what we're doing, because that's about putting in a 4th circle that's tangent to everything, rather than a circle that goes through the points of tangency. So 1, 2, 3 in here. But, so what could the result possibly be? Yeah, what am I expecting it to be if I have 3 circles and I put a circle through the points of tangency? Something like it's possible to do that. But and it's possible to do that because it's just going to be the something center. Which center is that? So if you have 3 tangent circles like those black circles in that picture, I think you can always find a circle through the 3 points of tangency, which is fine because that's just the circumcenter of those 3, the circumcircle of those 3 points. Draw in the triangle like we just did in Desmos, send 3 points through them, send the circle through those 3 points of tangency, with the result being that, is it definitely at right angles? It's definitely with what at right angles? So, so what I'd like, I suppose, then is slightly more powerful, right? I'd like to say that the circle that goes through those 3 points is actually at right angles to all 3 of the black circles where it meets them at those points. I think that's true. Yeah, because this is actually just the... Right, diagram time. Can I have a copy of this? Perfect, love it. Reset the zoom. Perfect. CC by SA 3.0 license, Zhuang Wang. Thank you. I'm just going to quickly screenshot this and put it in Paint because I want to draw on it. This stream would not work without Wikipedia and clumsily drawing over the top of stuff. Right, so I'm interested in the circle that goes through points 1, 2, 3, and I think it does so kind of at right angles to these circles that are already there. So in general, if you draw 3 points and you put a circle through them, and you say, is that at right angles? You say, to what, right? To what? But there are some actual black circles in this picture. But I think it works because if you draw in the radius of these circles, then you find you've got sort of R1, R2, and R3. Then what we've got here is something like, what are these? The circle that goes through all three of these points is, gosh, the in-circle of that original triangle for the centers of these circles. It is just the in-circle, which is, it goes through those 3 points and is tangent to the sides of the triangle. So sort of the existence of the in-circle, which I'm not proving here. Let's see if we can fit the in-circle in. Oh, let's try and keep it circular. Oh, right, okay. I really thought holding down Shift would save me there. Right, there we go. Putting in the in-circle gives me something that goes through. Hello, Phobal Stream. How are you doing? I saw you've been live recently. Phobal Stream in chat is a streamer who does sometimes math, sometimes computer science, sometimes coding, things like that. Right, what have I missed in chat while I was doing that? Yeah, so this triangle joining the dots might not be right angled in general, but it does meet these circles at right angles, which is sort of mysterious until you draw in the kind of triangle behind the scenes. I love the idea of a triangle behind the scenes, actually, and think of this circle that I've drawn in as the in circle. So then the hard question, what's this circle that goes through tangent to all of those? That's what Descartes' theorem is like. Yeah, the radius is at right angles to... This radius is at right angles to the... Yeah, you have to draw in a little line. If you really want to convince yourself, you have to draw in a little line like this. That's kind of tangent to both circles. At the point where they meet, there's a line that's tangent to both, and the radiuses are both at right angles to that. And then you have to really think, convince yourself that that means that the radiuses kind of form straight lines of a triangle. You just give me about 3 times. Good. Request in chat to derive Descartes' theorem, which I've had a go at it before and it didn't go well. I think Descartes might be better at maths than me. So there you go. Is this relationship between the curvatures, which is not the radius, is it 1 over the radius? Yeah, 1 over the radius. Some relationship between them. Some squares. There's a factor of 2. There's a square on the left. I think I have seen it as a step question or something. Can we see if it's in the step database? Something like this has been in there. Right, so I'm in the step database. I quite like the step database as a place to find hard maths questions. Oh my goodness, what is going on here? This has been tagged as touching circles, but I can't see where the circles are. Here's some curvature. Why are we differentiating this? All that's for non-zero. Oh no, it's just going to be circles. Okay, fine. Complex numbers is a good idea, isn't it? I'm sure I've seen this as a step question somewhere. Maybe not. Might have misremembered. Lots of questions about circles in here. Sorry to go through these. I just think that if it is a step question, we should do the step question version. If not, I should probably try and write it as a sort of question like that so that we can do it together. I've got down to option 39, which is a question from 2018 about the Argand diagram. Rational points. Fun. Wait, is that rational points on the circle? Yeah, it's finding rational points. What's this step question doing? Hang on a minute. What's this step question doing? I know some people really don't like seeing step, but hey look, this maths exam has got stuff about rational points. So write down integer points on and non-integer rational points on the circle. Yeah, fine. Simplify this, random, sort of, and hence obtain a non-integer rational point on the circle like this. So what's this going to do when you multiply it out? What's the point of this? The cross terms cancel, so you get 1 and you get m, 1 plus m. So if I want this to be 2, then I can set m equals 1 and be good, because then I will have cos plus sine and sine minus cos squared. Non-integer rational point. M sine squared, m cos squared. I've got distracted by a step question. What's the point of this? 1 plus m. So if I set m equals 1, then I can generate points. But I knew that because that's the transformation, adding the points and finding the difference, which transforms. It's got a scale factor of root 2 in it. So what? Logarithm ranges. What are you getting at here? Am I supposed to think of times when these things are both rational? No, that sounds rubbish. What about if they're both... That doesn't work, does it? Do I already have one? Oh, so I could take my 3... So if I find some funky solution over here... Yeah, so I could take my 3/5, 4/5 solution and transform it in here to 7/5, 1/5, which works because 49 over 25 plus 1 over 25 is 50 over 25 is 2. Right, okay, it's just telling me to transform the previous part of the question. Good. Okay, this is less fun than I thought it would be, and it's just twisting things around. There's a scale factor of root m, so I can set these different things. Oh yeah, step stream. We've become step stream. Doesn't quite work, does it? Oh no! Ooh, everything moved slightly. I've now got all this gap around the outside. Disaster. And also chat moved a bit as well, because I broke broke chat at one point and had to put it back. Didn't fix it consistently. That's annoying. Okay, so for this one, x squared plus y squared equals 3. My idea is to do the same thing but set m to 2 and then try and guess a value of theta for which sine theta involves root 2 and cos theta doesn't. Is that hard? It's a bit hard. Not if my original point. No, that is my original point. Cos theta sine theta gives you points on the unit circle, and then this is transforming them. Yeah, so I want to take m equals 2. Wait, I haven't read this. Non-integers are 2 rational points. Oh, right, hang on, what am I doing? Oh, I think I'm allowed to have these things being integers. So plug in your favourite integer solution. Your favourite rational point on the unit circle, transform it like this. Add them with a root m in there, subtract them with a root m. I think that's good enough. With a 2 in there, that'll give me some root 2 stuff. How do I do this then? Non-integer, 2 rational points. So m equals 10 is probably not going to cut the mustard, is it? And then there's a hyperbola. Fun. Same transformation though? Subtly different transformation perhaps. Okay, right. I'm now bored of the step question as well, unless I start writing stuff down. And also I feel like I've got distracted in 3 ways. I feel like I may have gone down 3 separate tangents to get to here, pun intended, with some tangents to circles. I ended up over here. Right, oh, and it's 20-3 already. Right, okay, I should get back on. This looks fun. I will store this, I think. How much of this do I want? I want this much of it. We'll store this. That was good. That's fine though. Store that for another time. Descartes' theorem, I think I'm going to leave it on stream as a thing for chat to think about. If you're not keen on number theory, although it does help you produce these kind of nice patterns, so that's fun. There's a section of Wikipedia that also tells you where to put the center. So, wow, crikey. Goodness me. So if you want to get your computer to draw incredible pictures like this, but with lots and lots of circles nested together, going inwards all the way in, some sort of a Apollonian gasket kind of thing. Ooh. I'm trying to find a picture, but never mind. Okay. Good. Wait, hang on. This says that Descartes did not prove the reasoning through which he found it. What? Did not provide reasoning? Probably did prove it though. Seems unlikely you'd make it up. Ooh, inversive geometry. Okay, right. I'm getting a little bit more distracted by Descartes' theorem because I think it's cool. One day I will understand this. Maybe not today. And then I'm back on Desmos, where back in Desmos land, we've discovered this thing about circles and tangency to here. But I don't think this is helping me with any number theory, which was supposed to be what I was doing today. Yeah, why not say? I just worry that I don't know. I worry I don't know where I'm going with it. It's just. I'll try and find a good resource. I don't know. So Wikipedia here is not giving me enough. The tempting thing is to write down a load of equations and then not be able to solve them. And I don't think that's very interesting. So I might just let people do that at home. Maybe definition chill maths is just write down some equations, fail to solve them, refuse to elaborate. That'll do. Do have time and tea. It's such a good theorem as well, look. What's pencil of circles? What? What? Oh, lovely. Okay. What? Any two circles on the plane have a common radical axis. Oh no, this is such a Wikipedia a trap to fall into. Oh, that is a cool picture though. Maths teacher has been in between streams. Finished a topology book. Well done. You've done all the exercises. Book has a lot of exercises. RFL. It's what we say when you get to the result you wanted. Is this some sort of projective geometry thing? What? 5 types of pencils. I don't have time for this. I'm going to go back to the safety of the fairy diagram, which is where I thought I would be. And then I'm going to find out what's in the book. I'm going to map out all of the stuff that I really want to be doing, and then I'm going to try and work out what on earth I'm doing. Goodness me. Right, continued fractions happen to be something that I've looked into before. So I'm going to skim through continued fractions, I think. Oh no, they have a new notation for them that I haven't seen before. Okay, with a sort of arrow, fair enough. So I'll have to remember that that's how they might start writing this as 1 over and continued a2 plus 1 over. Okay. And they're kind of up and down a little bit, superscript, subscript a tiny bit. But that's how they write fractions as well sometimes. Okay, so 2 and a bit, 2 and 1 over. Okay. Yeah, I've seen this notation before where you just write down the quotients on the way down. Are they quotients? Yes. More suggestive arrow notation. Okay, cool. Yeah, so you do this Euclidean algorithm. There it is. Brilliant. Love it. You get some partial quotients. Classical uses to find the highest common factor. Okay. You could factor into primes instead, but that takes ages. Factoring is hard. Finding common divisors, greatest common divisors is easy. 3, 2, 4. Right, okay. Right, this is what I want to do, I think. This. Because I'm sometimes in this position where I have to explain the Euclidean algorithm to people. And if this is a cool way to visualize it, then I think I'm interested. Or what is this going to tell me? Let's find out. So 9 over 31 is less than 1. It's 1 over about 4, but actually more like 3.5. But when I say a half, actually more like 1 over 2.25. That's how continued fractions work. This is sort of increasingly good approximations to your number. There's nothing at the front, so 9 over 31 is not as big as 1, but actually it's like 1 over 3, or maybe more like 1 over 3.5. And when I say a half, actually 1 over 2.25. And when I say 4, I do mean 4. That's how big 9 over 31 is. It's got a sequence of improved descriptions nested downwards through the denominators. A bit like a third, but better than that. 1 over 3.5. A half, more like 1 over 2.25. Yeah. Okay, 3, 2, 4. Enough joking around. What is this? Oh, I skipped a bit, didn't I? So now I'm never going to be able to know what's going on. Oh my goodness. You're going to do some counting. 1, 2, 3. 3, 2, 4. We use these three numbers to build a strip of 3 plus 2 plus 4 triangles grouped into these fans like this. What? 1, 2, 3. 1, 2. 1, 2, 3, 4. Oh my goodness, what are these? 3 over 10, 5 over 17, 7 over 24, 9 over 31. Where does this come from? Begin labelling the vertices of this strip. On the left edge, we start with these. Okay. So it's kind of a fan that way up, and then a fan that way up, and then a fan this way up. And we use the median rule for computing the third label. So this is the medians of those things, which just means adding the numerators and the denominators. And then the next one you add it again, and then that one you add it again, add it again. So what's going on here? Adding, so increasing the denominator to get that 3. And then what's this? So this is going to increase both the numerator and the denominator as you go over here. And then over here, numerator and denominator increasing by 2 and 7 respectively. Okay. What's going on then? So we end up with 9 over 31 at the end. That's, I think, the challenge to understand. This diagram has got something to do with the process of finding the continued fraction for 9 over 31, which is just like running the Euclidean algorithm on 9 and 31. And they're in lowest terms. So I would say that running the Euclidean algorithm gives you the highest common factor, which is 1. But here I know that the fraction's in lowest common terms in pictures like this. So if I say you have to start with a fraction in lowest common terms, I know that you're going to end up with 1. So I can start building my picture from 1 on the left and maybe have some chance of getting back to the fraction that we started with. That's the thing I'd like to understand, I think. Okay, used a mediant rule. I'm sort of getting to grips with the mediant rule as kind of more of a storage method, right? The fact that they're written like fractions is not quite related to how the mediant rule works. The mediant rule is you take your two fractions, you just add the numerators and the denominators. That makes me think a lot more like adding vectors or just having two separate bits of addition that are happening, rather than anything to do with fractions. But the final thing is formatted like a fraction, so I guess that's why we're talking about them like that. Okay, may seem like just an accident, it does at the moment. Nevertheless, theorem 2.1 is going to show us that this always works between 0 and 1. And then for fractions bigger than 0 and 1, you have to start with 0, 1. Replacing the numerator 0 of the label 0 over 1 with a0. The initial integer in the continued fraction 0 over 1 is replaced by a0 over 1. Oh, so you put this down here. But isn't that just... Isn't that a little bit like if I said you start... Can you do that with a sort of fan though? Because... What would I put over here? I want you to do twice. I want you to add 1, 0. So I guess this was 0, 1 over here. Yeah, why not just start like that? With an upside down kind of fan. That's what's down here. So I think my rule is I want to put the 0, 1 in. That will be part of the system. Yeah, fine. Okay, it's basically the same thing because I think the last step of the Euclidean algorithm is kind of the same as the previous ones. So, oh well. Okay, is it the same? Who knows? What am I talking about? I'm trying to work out what's going on before they tell me in theorem 2.1. So it's coming up anyway. But part of paying attention is to try and work it out first. So what is this? 14 over 5. And something's happening 4 times. So if I think about coming down from 67 over 24, what's happening is that something's being subtracted. It is 5 and 14. Why? Why? What's special about that? Because what would I do if I was doing 67 divided by 24 to get... Oh no, I'm not supposed to do that, am I? Because that's giving 2, which is something over here. This is like the end. Okay, so this isn't the first step of the Euclidean algorithm over here. The first step's over here. Interesting. Interesting. Here's the opposite process, where it's got this bit that I was thinking about for 2 over here. And then if you go with 1, 3, 1, 4, it's just the other way up, isn't it? Well, the fans are the other way up. The numbers are all the other way up. Other way up. 67 over 24. 24 over 67. That's the other way up. You learnt it here first. So, okay, so we're starting from this end, which is a bit surprising to me, because when you normally do the Euclidean algorithm... Oh, am I being an idiot? Maybe. We'll find out in theorem 2.1. So when you do this kind of division, you say, well, it's about... You do 67 divided by 24, and you say that's 2 plus a remainder. So it's 2, to keep track of that, there's 2 here, which says, aha, add 1, 0, add 1 to the numerator, add 0 to the denominator, twice. The opposite, add 0 to the numerator, add 1 to the denominator. But do it twice, because the denominator here is 67 is about twice as big, plus a bit more. I've got more instructions coming. So if you do that twice, then starting from this thing, which looks like infinity, don't panic. adding 0 and 1 twice, you get to 1 over 2, which is our kind of first kind of approximation for 24 over 67. What next? So I like this. This one's upside down because we're now working down in the denominator, maybe something like that. To say actually, down here, this 1 means that one time I would like you to add that fraction we were just talking about onto 0, 1 to get 1/3. So that takes us from this this convergent, which is 1 over 2 plus 1 over 1. So sort of this much fraction evaluates to 1/3. It's another approximation of the fraction that we've got. These are great for approximating fractions. Something you can find out about continued fractions. Over this way, I'm adding 1/3 lots of times. Why am I doing that? Why am I adding 1/3? Well, I'm not adding, I'm doing the median rule to 1/3. So I'm saying you've got 1/3 plus what's the remainder? So this remainder is going to turn out to be 3 down here. But what am I trying to do? Any more would go past the number. So it's something like there's somewhere in here, after some rearranging maybe, there is still a kind of quotient remainder thing going on. But 3 is the quotient for how many times can you do this process until the fraction itself gets too large, I think. Algebra, maybe. So something like it's upside down at the first step. So you've got this 2 plus reading here, which is what I would expect it to go 2 steps. And then I've got this, so it's kind of like why do I want to do any adding going this way around? We'll get there. We'll get there. Okay, so the mystery for me is why, after you've done a few of these steps, the quotient for the next division has something to do with adding, doing the median thing, adding lots of times. I can kind of see they're related. There's some sort of quotient theme in there that when you do division, if you say 67 divided by 24, roughly how large is that? You could do that by subtracting 24 a few times until you get down to something that's smaller than 24 but bigger than 0. Like, counted how many 24s literally go into 67. So one way you can do it. What is that diagram? Oh my goodness. Is this more observations or is this a proof? Yeah, good. It is the convergence. I think I said that out loud by mistake. Yeah, 4 over 11. This one's good as well. And then 5 over 14 and then 24 over 67. Good. Values of terminal segments. The terms to the right of each plus sign. Yeah. These are the fractions one computes in order to find the value of the continued fraction. Hello, Wazzers Mazzers. Great username. I know one programming language which is not very good. And I'm trying to learn a second. And I've ambitiously picked a second that's basically the same as my first. Oh wait, no, I've remembered a third. 2.5. 2.5. With work on that third one. Yeah, the list is terrible. I learned MATLAB first as a starter language, and then I refused to move on, and I did everything in MATLAB, and that was fine because I was writing slow code, but I was also writing it slowly, so it didn't really matter. And then I had to learn some Fortran because I had some Fortran code that I needed to work on, but luckily for me, Fortran is almost the same thing as MATLAB, and now for grown up, got to try and do things properly, got to interact with other people's code, finally trying to learn Python. But it's taken me a long time to actually get to the point where I want to use Python to do anything because it's still so easy to just chuck it in MATLAB. So that's my 2.5. Good question. Welcome to chat. This is Chill Maths. Right, there's an exciting picture on the left with lots of semicircles jumping backwards and forwards to work out what's going on. I suppose I have the option at some point. Where's this? It goes 3 over 8. What is this? There's an option at one point. if you get really good at Fortran, there's not very many people who are great at Fortran. So I guess a different career path for me would have been to actually get good at Fortran and then, I don't know, do maintenance on old telescopes and things where the code's in Fortran. You know, I don't know if that's still true. Maybe they're not using Fortran anymore. That would be a big danger of learning Fortran, is that by the time you finish learning Fortran, is there any Fortran left that you need to read? Maybe there is. None of my opinions on coding languages should be taken seriously. Okay, this is a simple fraction, 3/8. We just had this lovely story about 27/64. We're now throwing it away, I think, for this story about 3/8. Shall I do the little continued fraction for 3/8? I think I should. So 3/8 is kind of smaller than 1, so I'm going to write nothing. I'm going to say it's 1 over, it's kind of 1 over 8/3. How big's 8/3? Well, 8/3, that's an improper fraction really, isn't it? You'd say 2 and 2/3. And then 2/3, that's 1 over 1.5. 1.5, you'd say it's 1.5. So you can work down like that. Oh, thanks, Murray. It's tea time. It's 3 o'clock. We've got a continued fraction that goes 2, 1, 2. Oh, I wish they'd picked one that wasn't symmetric. And there's something going on with these circles to get us, semicircles to get us from here to there, back in again. I'm interested to see what's going on there. Oh, it does make it look like it's this picture does make it kind of look like the numbers are converging in towards 3/8, which is exciting. I think this is just on the number line, isn't it? And then these arcs are showing us median. It's from the fairy sequence. What did they do? Oh, sequentially you put in the kind of midpoints in some sense using medians. So that's why there's these semicircles to 1/2. And then a semicircle to 1/3, which, yes, they've placed it where it goes on the number line. And then 1/4 and then 1/5. But also, I guess there should be 1/6 should probably be in this picture. Maybe not. Okay. I'm just going to read this, Murray, and then we're all going to take a tea break to get a cup of tea, refresh, think about what we're doing. Oh, what was that? I don't know what that was, and I've set the text to white. Oh, DNI Umagad has subscribed with Prime right now, this very minute. Says the interface thing. Thank you very much for the Prime subscription. That's right. It's very generous. That goes to charity ultimately. This stream is permanently in charity mode. So if you have a Twitch Prime subscription, you get one for free if you have Amazon Prime, I think. It's also reminding me to use mine somewhere. And welcome to chat as well. Hello. There you go. Subscribe with Prime and then join chat. Wow. Okay. I'm going to work out what the picture is. I think I can see the punchline coming. So I'm going to say what I think the punchline is. The punchline is something like, look. This is a distorted version of this picture on the right. That it goes 2 triangles this way. 1, 2. And then 1 back again, with a load of decoration stuff over here, but 1 back again, 1 around this way. Did I just draw that? I've confused myself. No, was that already there? What's that bit of arc? Oh, these have been marked in. Yeah, okay, this is exactly what they want me to look at, isn't it? It's 2 going this way, and then 1 coming this way, and then 2 going in that way, and then you have reached your destination, the fraction 3/8. So I think what they're going to tell us is that these kind of fan pictures where you change the numerator and the denominator along the way. So along here, adding numerator and denominator using this kind of almost like a vector addition, moves things inwards and gives us a version of this picture where you end up at the fraction you were looking for. These lines, in some sense, are lines that we've seen before from the fairy sequence, from the fairy diagram. We've seen a few things. Okay, thanks for redeeming tea time, Mary. If you've joined the stream, what we like to do about 3 o'clock is refresh a cup of tea. So you don't have to make yourself a cup of tea, but this is a good point to do so if you would like to. I'm going to be gone for a minute and a half, maybe 2 minutes. The screen is going to say back soon. You might see an advert. If you see an advert, you're supporting charity. Ultimately, the stream is permanently in charity mode. Thanks to Mary, who has sort of reminded us to drink tea. Also brought an ad break on us all. So let us know what ads you get, because I think that helps the algorithm. And I'll be back in a minute and a half with a fresh cup of tea. Right, see you on the other side. I'm back. What's going on? Oh, people got loads of adverts. Google Pixels, obviously the Lloyd's app, the NHS, and also, yeah, well targeted. Good. Don't tell them that. I mean, do tell them that if you want more adverts for Google Pixels. I've now said Google Pixel twice, so all of my ads are going to be for that forever. I think that's how it works. Good. Okay, before the break, I think we had... What did that say? Before the break, I think we had the kind of big reveal, medium-sized reveal, that the lines on these diagrams, which are constructed from continued fractions, are exactly the lines in this picture. Ooh, that is something to do with the Fourier sequence, joining together medians. And kind of course they are. These lines are joining together. They're made by medians. So we're going to get some medians or something. Right. The zigzag path becomes a pinball path in the Fourier diagram, bouncing backwards and forwards. Which I guess is related to the idea that this thing converges. That's neat. I guess you have to know that the medians appear in order. Yeah, fair enough. Sort of same things around. We just did the tea. We just went and made a cup of tea because Mary told us to. I think I probably tell this story every time I get a cup of tea. But in basically the first video I made for the university before we did live streams or anything for uni. We did a video about the maths test, which I filmed at home on a wobbly laptop. And the concept was I just showed people math questions, but I hadn't invented the technology of pause to try the question. So the video is mostly me sitting in silence drinking tea while you try a math question. This is where we started. The kind of original outreach video that I made for Matt was mostly silently watching while you have a go at home. No pausing, just runtime. And YouTube accepted that video. We uploaded it and YouTube didn't say, "What are you doing with our servers, mate?" It just told them to pause. They accepted a video that was mostly me sitting still drinking tea. And it's quite nice to have come round full circle in a way, to go more professional at work and actually fill the silence and occasionally instruct people to pause, but then start doing an unprofessional live stream and to come all the way back round to just sitting here drinking tea. Yeah, it's sort of circle of life, isn't it? Right, yeah, good. Some of my colleagues caught me afterwards and said, "Oh, great that you're making videos, but it's just you drinking tea." It's not. You could be. What are you doing? Oh well. And I thought the problem was going to be that the laptop was so very wobbly, which meant that every time I picked up or put down the table, I was in like the spare room. It was the pandemic. Everything we got away with it because it was the start of the pandemic and quality was much lower. Right. I did most of them. If we're going to talk about this, we should talk about the way that I did most of the Matt live stream like that for the first year. Matt live stream is the show we do for work where I give advice about the maths test. And these days it's quite organised. There are worksheets that get published in advance. The very first time we did it, I didn't have any worksheets, so I just picked some math questions, usually at the start of the show or just before the show. So no one had a chance to have a look at them beforehand, because I hadn't been organised enough to pick them beforehand. So then the format of the show was me drinking tea in silence, waiting for people at home to have a go, and then letting me know when they'd had a go at the questions. We didn't get a lot of questions done, but it was quite it's quite a different feel to the kind of modern way that we do the Matt live stream, where people have had a go before, people have got questions. We try and bundle through loads and loads of stuff. We try and sort of rush through and be helpful in lots of like different ways with revision material and looking at Matt questions. Part of me does miss the kind of tuning in live, just saying, "Oh, here's a question I think we should try," and then just letting people have time to do it. Maybe I should do that again. It was much easier. Okay, right. Enough of me moaning about my job. I should do my not my job. Oh, that's interesting. That notification means that I've got Steam open. Let's fix that. Quit Steam. Cool. I got one of those. Your friend is now playing notifications. Luckily, it was on my other monitor. Haha. Professional streaming. Uni problem classes. Little bit like that. Got to give people time to do stuff. And if nobody wants to say anything, then it's going to be very quiet. But I've got tea. We could put tea back in the professional streams. I have occasionally. I can't leave during the professional ones. So it's whether or not I remember to make a cup of tea before we go live. Right, that's now too much behind the scenes content. There's Theorem 2.1. I've been waiting for Theorem 2.1. It's just appeared. Did you see? I scrolled and there it was. But before then, I've got some observations to read. Right. Convergence alternately smaller and larger. Lovely. I like the visualization. I think that's very nice. That's a thing that I've seen proved before. But with the kind of pinball path, lovely stuff. With the pinball path, you can see it happening. You can kind of see the things going left and right. You know that kind of, is this why it's called topology? Maybe the things contained within that the arcs. If you understand that the arcs don't cross each other and that they lie within each other, then you're kind of bounding how far it can bounce on each pinball path going down. Maybe that's an idea. The triangles that form the strip of triangles of P over Q are exactly the triangles in the Faro diagram that lie directly above the point P over Q on the x-axis. You've got me there. above the point on the x-axis. Above? What? Help, chat. What do they mean above the point P over Q on the x-axis? The x-axis is the horizontal one. The triangles that form the strip of triangles for P over Q. Oh, they mean above. Sorry, chat, I got there first. I did some audience interaction, but then cancelled it immediately. They mean above. So, like, if you look above the 0.3/8, I've messed that up a little bit. But above the 0.3/8, there's triangles that go through that airspace. The big one above, massive, goes out to infinity, and then these ones. So if you look directly above 3/8. Yeah, so I was confused. Above the, so it's above, and then there's kind of brackets. They don't mean above on the x-axis. They mean above this on the x-axis. Okay. The strip of triangles considers triangles that the vertical line through the vertex P over Q crosses. Should have read that. Should have read that. The problem for talking through these is that it's always the case that reading one more sentence would improve my understanding to the point where I don't need to ask a question out loud. The question I'm asking out loud is almost always answered by the next sentence that I haven't read yet. But if I just read the next sentence, then I'll never say anything out loud. So I have to say all the stupid stuff out loud. That's like the millionth time. Okay, right, I'm very cross with myself for not just reading one more sentence, but also it doesn't work like that. You're watching at home, right? You could see the next sentence. You can look down to the bottom of the page. I have to be really careful because I just scrolled. So I scrolled and 5 more lines are now visible on the screen to people watching, but I haven't read them yet, so it could say anything. It could say like, it's like having a kick me sign on my back, right? I just keep putting the stickers on. What do they say? Right, I'm reading it now. You've already read it, but I'm reading it now. Here we go. It's theorem 2.1. The convergence with a continued fraction, which is the kind of approximations that I mentioned before, are the vertices along a zigzag path consisting of a finite series of edges. This is describing the distorted kind of triangle stuff in the fairy diagram, starting at 1/0 and ending at P over Q fraction. The path starts along the edge from 1/0 to A0/1, then turns left, across a fan of A1 triangles, then right, also to left and right, and finally ending at P over Q. And that contains within it the fact that I'm interested in, that this process actually stops. With these numbers, the quotients is how many triangles you have in each fan, actually gets you down, actually leads you to the correct point, like a kind of treasure map or something, leading to you to the 0.3/8. That's the right, you use the quotients on the way down. I'm expecting to see some like kth line of the Euclidean algorithm and comparing that to how to get through the, I think it's backwards, so maybe not the kth step of this process, but the n minus kth step or something. What have we got? Oh, look, there's a big process where the ith step is labelled AI, but this is going to be something to do with, oh my goodness, what is going on here? Something to do with this ith step. I'm expecting to see Euclidean algorithm somewhere, but I don't. It's going to be 2x2 matrices. Okay, fun. Let's go. It's good to predict what you think the proof might involve. I'm always wrong, but it helps me identify which bits are surprising. Diagram like this, which is maybe the most obvious visual thing on the page. Not surprising, right? We're talking about a long process. We want to talk about a general step of the process. You have to draw something like this, don't you? Or the other way up, or I don't know. Let's have something like this to talk about a general step of the process. If just following the steps would give you something like this, loads of ... in between, love it. But you've got to show that you get to this thing P over Q at the end. There you go. So this is equals P over Q at the end. So something like, you're going to have to convince me that along the way you're getting, I don't know what these things are though. I don't understand. They're not the, I mean, they're the convergence, right? So you're going to convince me you get the next convergence somehow, that working downwards you've got convergence. Doing the Euclidean algorithm gave you things that were a bit like convergence, but listed from, I'm just really confused that I think you go right to left when you do the Euclidean algorithm. Maybe not. Maybe I'm overthinking it. Maybe I'm overthinking it. Yeah, you go left or right, don't you? You go both left or right in both cases. That's why they're going to match up. Okay, I think I've identified my misconception. The first step of the Euclidean algorithm is to compare how large the numbers in front of you are. And that gives you a quotient, which would say an integer if it was the fraction was approximately an integer. That is the very first step. Both in the world of convergence for your continued fractions and also in the world of doing the quotients of the Euclidean algorithm. So I think these matrices are just going to convince me that the Euclidean algorithm works. We'll see. Okay, right. Talking. Brought to you. So much talking, not enough drinking tea. Okay, here's the this formula works by using the median rule lots of times. It's this thing that we've been trying to follow, drawing these curved arrows around to say, to get from here to here, you do the median thing using this one lots of times, A2 times, so adding P1 and Q1. So where is this? Which is sort of, if you're down here, well, we need to add this, not as a fraction, but to add the numerator and the denominator on AI times. So that's what's happened here to get up over here. Median rule being applied that many times. Good. Right, so what is this going to tell me? I don't like that it uses the previous two. Oh, yes, I do. That's what the Euclidean algorithm does. But there's two things going on, right? There's Q's and there's P's. It's not going to be quite just... maybe I was expecting this line to say, aha, that's the Euclidean algorithm for the numbers P and Q. Maybe that is what's going to happen. Oh my goodness, look, it's just matrix products. Good stuff. Hello in chat. They've just joined and they know who Mean Machine Rex is. Good stuff. Welcome to chat. Famished edits. It's always fun working out where to put the spaces in people's usernames. Mean Machine Rex makes it easy by using... It's not quite camel case, is it? But the other one. But, you know. Cracked the code. Right, here's a big matrix product. They go so this way up and then that way up and then that way up again. Ooh, the first term really is different. Oh, that's a bit surprising. The first term really is different. We can multiply this product starting from either left or from the right. This one, so the columns give you these. Is this like that Fibonacci thing we were talking about? Multiplying the first matrix by the second matrix gives this. Right, matrix multiplication, let's go. 0, 1 gives you the second column. 1A1 gives you this much, which is... Oh, okay, that is P1, Q1 because of this quotient rule thing. Yeah. So these are convergence for the continued fraction. How do I feel about this matrix stuff? It sort of feels a bit like it's that tabular way of doing the Euclidean algorithm that Chat told me about last time, which I haven't looked up, so maybe I should go and look that up. There's the extended Euclidean algorithm, which feels like basically the same thing. Anyway, doing this multiplication. Keep multiplying, you will keep getting the convergence. So I think this matrix multiplication is somehow capturing this process. Let's think about that a tiny bit. So if I copy this out, is this going to work? What do I want? Something like I minus 2, pi minus 1. So if instead of fractions, if I treat them as kind of bits of a matrix like this, and then I multiply it by... So what's happened here is upstairs, I just want A1 times the first column, and that's what I want. And A1 times the second column and 1 times the first column. That's what I want upstairs. How do I achieve that? So is that what you get if you... So along the top here... No, what do I write in this matrix in order to achieve this kind of effect? So I should be looking at this column, and I should say that I want A of these. No, not A of those, one of those. I see, so one of those, and AI of the P's, and that works downstairs as well. I want AI of the QI minus ones and just one of the previous ones. And then, because this is using the previous two terms, this 0, 1 bit is preserving for me the previous thing. But not the one before, that's gone. But this 0, 1 extracts the right-hand column and places it in the left-hand column. We've seen this trick when we were talking about using matrices to generate Fibonacci numbers. We had a trick a while ago for just sort of taking a column. I'd like to keep that data for future use, and so hold on to it. 0, 1. In fact, this is all the same thing, isn't it? Because the Fibonacci numbers come from the Fibonacci numbers are convergence of the continued fraction of the golden ratio or something. Maybe 1 over the golden ratio. I'm going to stick with my guns and say golden ratio, which means that the Fibonacci numbers should fall out if... No, the Fibonacci numbers aren't the convergence. The convergence of ratios of Fibonacci numbers. Something like that. Excuse me, so that was quite a slurp. So I think if I set all these numbers to 1, then you get the Fibonacci numbers, which is something we've explored before. And sort of saying that, hey, do you know the continued fraction with all ones going down? That's the golden ratio. Maths 22222. I don't know if you're still in chat, but the continued fraction with ones going all the way down, 1 plus 1 over 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 1 plus 1, that's the golden ratio. That's something that I think we've discussed that problem before. This kind of slightly surprising result, that this kind of continued fraction where you keep going 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, I feel like we've had a conversation before where that's turned out to be the golden ratio. Which is a nice way of writing the golden ratio, my word. So that's a continued fraction. And there's also a slight clue that you can use continued fractions for irrational numbers as well as rational numbers. If you truncate it, if you stop doing it, then you get an approximation to this. So this is related to some things I care about, isn't it? So that could be a way of generating good approximations to phi or root 5 if you prefer. What's the rule here? So if you want just to put that into a kind of maths puzzle or something, the convergence to this continued fraction in the fairy diagram, we're bouncing backwards and forwards using the median rule to keep adding. If you keep adding, you're doing something a bit like the Fibonacci number rule. So what do I want to do? I want to tell you then, as a kind of weird fact, that you can get approximations of root 5 by roughly doing, so what do I want to do here? 2 times a Fibonacci number divided by the previous Fibonacci number, because that's about golden ratio, 1 plus root 5 over 2. So if I multiply by 2 and subtract 1, then you get root 5 more or less. For example, if I take two Fibonacci numbers, 144 and 89, and take off 1, what I get upstairs is 288, take off an 89 is, do I believe this? Is this working? 288 take away 89 is 199 over 89, which I claim is about root 5. Heaven help me, I've opened a calculator app. That looks like it could be about root 5. 2.23595, yeah, root 5. Should we calculate root 5 as well, just to compare? It's pretty close, isn't it? 2.236, 2.235955. That's pretty close. And that was just using small Fibonacci numbers. So there you go, okay. If you want an approximation to root 5, you could do something like this. If you want to make it better, you could use more Fibonacci numbers. Hello, Ed Stucky. Time zones. Maths Tutor 2 has got another one in chat, which is to do 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, which I can't remember. Does that one give exactly root 5 or something? Yeah, continued fractions, I know. And the fairy diagram, this diagram, let me show you. So we've got these arcs in the diagram. They're constructed in a hierarchical way. I don't know if you've seen this before in Stucky, but stop me if you have. So you start with 0 over 1 and 1 over 1, and also these weird ones, 1 over 0 at the top. And you calculate, for everything you've got, you calculate a kind of midpoint, which instead of being at the numerical midpoint, you add the numerators and you add the denominators. Exercise, that gives you something in between, which is, in the first case, 1/2. And then to build this in, so the midpoint of 1/2 and 1 over 1 is 2 over 3. So there's this point in here, and you draw these arcs in. And then the punchline is that these arcs you get are precisely related to the quotients in a continued fraction. So you can follow the path inwards. If you know the continued fraction, you can read across. So 2 arcs this way, followed by 1 arc inwards, followed by 2 arcs in that way, gives you kind of 2, 1, 2, gives you the continued fraction for 3 over 8. And you can use this to maybe prove that the convergents actually converge inwards, above and below. I think it's the first example of this kind of diagram. The whole book is about this kind of diagram, to join in these points connected by the mediant rule, where you add the numerators and add the denominators. Cynic in me thinks that secretly behind the scenes, adding the numerators and denominators of the fraction is not the right way to think about it. Actually, the right way to think about it is some sort of matrix operation that's happening to the pair of vectors, but whatever, we're having fun. Yeah, continued fractions suddenly everywhere. Also, root 5. And Maths Tutor 2 has sent me a question in chat, and I'm trying not to get nerd sniped by it, but it's not working. Here I go. What is that then? 2, 2, 2, 2, 2, 2, 2, 2. So if it was 2 at the front as well, so your number x plus 1, if I add a 1 to it, then I get that. Okay, have you just done the thing that's 1 plus 2 over, then this would be, and that would be x plus 1 as well, with the 2's down here. So something like the one in chat is something like, well, forget the 1 for a second. U is 2 plus 1 over u. What have you done? What have you done? B squared minus, I'm so bad at the quadratic formula these days. That's very embarrassing. 1 plus or minus root 5. I think you fixed the factor of 2 for me, haven't you? B squared 1 minus 4, 2, root 2. No, I'm wrong. You fixed it so it's root 2. I think. Is it root 2? I think it's an exercise that I once set for you and then forgot about. And I'm unable to do it while also streaming, despite the stream being a chance for me to do that sort of thing. Right. Good, I said root 2 before I erased everything. Thank goodness, right. Pebble Stream once calculated 100 billion digits of square root of 5. Using this method, did you use a continued fraction? I guess that would be quite a good way to do it. There's other ways available. A fun one is if you want square roots. Let's do it. Can I do a blank page? They've added a tool where I can add a blank page, I think. Let's go. Can I do? Yes, new note page. So one that I've seen that I really like is if you want the square root of 5. It depends how fast you are at dividing. If dividing is hard for a 100 billion digit number, then don't worry. But this function is fun because applying f multiple times converges to root 5 quadratically or something. So if you can calculate 5 over x in constant time for a given value of x, which is a bit dubious, but if you can do that, then this converges quadratically, which I think means every time you apply it, you get twice as many digits. which sounds a bit stupid, right? Like you have 100 digits of root 5, you plug in that number into this expression, and now you have 200 digits of root 5. You do it again, now you have 400 digits. It sort of doubles each time. Divided by 2 is fine, yeah. It's this bit 5 over x that I'm really, really scared about. Where if x is 100 billion digits of decimal number that you're somehow storing in memory, then working out 5 over x, I'm a bit worried that I'm leading you down the wrong route. But I'm worried that might take time 100 billion to achieve. I suppose you want as few operations as possible using your 100 billion digit numbers. Maybe. This is on a question sheet that I've just seen for this term. A course that I'm doing this term has got this one in it, which I like. There is a version, I think, which converges quadratically without using division. Let's see if I can work it out. Maybe I should prove why this one works. Don't know. Not going to. Is it even true? Have I done it right? The idea is it's the midpoint between these two quantities, and it'll stop changing when they're equal, which is at root 5. Well, no, hang on. Stop changing when they're... Stop changing when... Yeah, they're equal, because then their average will be the same again, and it'll return the same number. Excitingly, it actually converges near root 5. There's some caveats about where you start, I suppose. Don't start at 0, but it's pretty good. I have some terrible Python code that I'm not going to put on the stream for that. We're getting a tiny bit distracted. Can I remember the rule for... Let's see if I can work it out. The trick here is to think of a function where f of x equals x at precisely the value I care about. And there are some more terms and conditions for whether or not this actually works in terms of whether it converges and whether it does so particularly fast. But yeah, so I think this is actually Newton's method, isn't it? This is Newton's method on the expression. So if you have the curve x minus 5 squared, and you want to find, no, x minus root 5 squared or something, x squared minus 5, there you go, that'll do. And you want to find, so you have x squared minus 5, and you want to do Newton's methods to find this root. Well, Newton's method says that you should calculate, Newton says that you should calculate your new value should be x minus, and then f of x divided by the derivative, which gives you exactly x over 2 plus 5 over x. So it's Newton's method on this quadratic, which is why it's quadratic. Unfortunate coincidence of words. It's Newton's method applied to this parabola. Newton loves parabolas. And Newton's method is quadratic, not just for parabolas, but for functions in general. Smooth, whatever. Newton's method is quadratic in general, so you get quadratic convergence, which is kind of nice. The trick is to choose a different function if you want convergence. Oh, is that a staircase thing? Thank you. That's do. It's some sums. I was hoping for a plot. No, never mind. Okay, yep. You can check that in Desmos. There's this kind of spider diagram that you learn to draw in A-level if you're in the UK, and if your A-level syllabus has it in, because I don't think they all do, where you keep applying F. There's a reflection step in that, which we could talk about, because it's kind of related to the stuff that we've been thinking about here as well. So this function, f of x, is and up. This is f. So what you do is you evaluate f, and then to get that round again, you go across to the line y equals x and down, which sounds mad, but does take you from the point where you had the value on the y as the y coordinate, you read across so that the value is now both coordinates, and then you read down so that the value is now the x coordinate, and then off you go again. And so I suppose that means you evaluate the function. So what people actually say is you go across and then you evaluate from there. So you kind of step in and down and in and down. That's a terrible picture because it's already converged really quickly. Where I started over here, move to the line, evaluate the function, move to the line, evaluate the function, and move to the line. And we're ending up over here. The spiral thing from A-level, right? Except even better for this one, it's not even spiraling, it's just going in really quickly. Newton's method, very good. Newton's method, the kind of derivative one, where you say, what if my function was a straight line? Then I would be already home. If I just did this, I would take the value and I would correct for the straight line thing that's going on. And that's this expression, which drawn in the kind of looking for the point of intersection with f of x equals x. I guess we're putting y on the graph as well now. Gives you this kind of repeated way of going in. Other functions are available. I'm going to try and remember one. That's a bit of a bold claim. Let's see if this goes. There's one that involves addition and subtraction only. It was on a question sheet that I did once. Maybe the fastest way for me to do this is to look up the question sheet without showing you all my documents. So this is an exciting thing to be live streaming. I'm going to talk at the same time. I'm going to read out chat. I don't know what Householder's method is. Ooh. Higher order derivatives but slower computation. Oh, is it a correction and a better version of Newton? You start with the same shape, root finding, but is it a better root finding algorithm? Oh, now I'm going to Google that. Wait, no, I'll let Phobos Stream can tell me if it's a better root finding method. And then, Maths made the spiral thing already. It's all happening. Here we go. Teaching constructive maths. Is that where I saw it? Sheet 3, maybe? Sheet 3. Sheet 3. There we go. So, question from one of the constructive maths sheets from a couple of years ago. If you want to do division quickly. Oh, that's not fit on screen at all, has it? It's marked optional but easy, which is where we want to be for chill maths. Reminder, the stream is optional but essentially easy. The question one harder, strictly optional. There you go. That's not what I'm up to today. So this is division, which I'm worried about. To find 1 over a, because for part of that I needed to do 5 over x really quickly. But there's this application of, you can use Newton's method for that as well. Thinking about f of x is a minus 1 over x, because that stops when does that stop? Oh no, so root finding on that function, that's 0 when x is 1 over a. Okay, so I'm going to think about that now. A minus 1 over x. So different function. I'm going to call it g, I think. I'm going to forget about the 5 for a second. I'm going to forget about x. It's kind of your previous number. To repeatedly do this function, you need to do 5 divided by x. So if you want to do that, then you just need a couple of steps of this function, which is going to be, so to find 1 over a, you need that's defined by a minus 1 over x. So if you do this, I could put a 5 in here somewhere, couldn't I? But I'm not brave enough. Multiplying by 5 is definitely easy. So a minus 1 over x. A minus 1 over x. Because then Newton, for that, says that what you should do is you should do x minus the value divided by the gradient of that thing, which is 1 over x squared. So if your previous guess for what 5 over a was like 1, don't know, it's not a great guess, but we'll try. Then you should put the number 1 into this expression. And brilliantly, this thing simplifies. I had to look it up, but we did get there. So is this plus another x? What is this? Is it 2x minus x squared? Okay. Just in time, Maths Tutor 2 has made a root findery thing for me, which will let me demonstrate that. Is it going to do some sort of algebra? Let's find out. So here's my g of x. Which one do I want? Oh, it's going to show me lovely, lovely, lovely stuff. Good. Okay. G of f of m minus 1. What is this? So it's going to keep doing the previous. Oh, right. Okay. So this is Maths222 taught me this in chat before. This is a way to get it to do all of the evaluations, right? It's like a case-based thing. If n is 0, then it returns 1 as an initial guess. Otherwise, it applies g again. So this is a way to calculate g lots of times. My idea is to do 2x, interesting, minus, what did that say? I've forgotten what that said. Ax squared. So if I want to do, okay, so if I put 5x squared, that's pretty bad. What have I done wrong? Maybe I need to do small numbers. Okay. Right, so if this is finding 1 over 0.1 is the number 10, which is it's found by zigzagging over there. If I want to find 1 over, I don't know, 1 over some small number, then it can do that in a few iterations over there. And importantly, if I have lots of numbers in here, it can do this calculation just a few times to calculate 1 over that thing I'm typing in nice and quickly. Okay. It seems to struggle with finding 1 over large numbers, which is a bit of a problem if you're trying to calculate the square root of 5. That's right, famished edits. We've got football stream in chat as well. It's a sort of streamer event. Biggest since Marvel Cinematic Universe got together. There you go. Right, okay, what are we doing? We were definitely doing something. We're root finding. I'm not certain that this is actually good news for football stream. I don't know how division works in a computer. It's possible that division is really, really slow. If you need to do 5 divided by x, and x is lots of data, then me saying, whoa, you just do 2x minus that thing x squared a few times. Like maybe that's also impossible because you've got to do multiplication by, in this case, a is the thing that you're trying to divide by, is this thing in here. I'm using x for everything. Whoops. Maybe that's not good news because maybe multiplication is just as hard as division. They both seem to be, I would guess, they would take about, if your number is 100 billion digits long, they would take probably time proportional to 100 billion to do either of those operations. Don't really know. Someone with computers, a quantum computer, sure, it can do it straight away, one step or something mad. But yeah, it seems to me if you're storing 100 billion digits and you want to construct something new that's 100 billion digits, it's going to take ages, isn't it? If you're going to write 100 billion bits of information, however you do it, just writing the answer is really slow. I don't really understand this, like, order. Sometimes the order stuff, sometimes I really get it and I understand how doing fewer steps is good. But if each step is also really, really hard, then I feel like we've just cheated and pushed it all to there. Right, yeah. Big team up movie. Have you heard that Apple TV have made a TV show about mathematicians? It's called Prime Target. It's a mathematician solves prime numbers, and now that governments are out to get him, and you can watch that on Apple TV, not sponsored. He starts off in Cambridge and goes on adventures. Yeah, so that's he solves them all. He's found, I think, in the trailer, he's found sequences in the prime numbers. They don't say what sort of sequences. It's not the Green Tau theorem. It's not fun sequences. He's just found sequences in the prime numbers, which is quite surprising. I mean, it's also not surprising at all, right? Like, sequence of prime numbers, a sequence in the prime numbers. Right. But if you like maths thrillers, then there's only a few, so it wouldn't be a very long movie night. And now you've got, I think it's about 8 episodes of Prime Target. The name is perfect. The name is very good. I have no notes on the name, except Amazon Prime have got to be kicking themselves, right? That they didn't purchase the TV. It's gone to Apple TV. Haha. Really, it should be Prime Target, brought to you by Amazon Prime. Apple TV brings you something about Newton. It'd be just perfect, right? Their logo even used to have Newton on it, I think. Maybe someone will fact check this, but I think the first version of the Apple logo has like a woodcut carving of, am I making this up? Woodcut carving of Isaac Newton sitting under a tree. That's what the apple is referring to. They could bring that home by having a crime drama where Isaac Newton solves crimes in like the Mint or in I don't know, high society of the time period, or Isaac Newton goes on an adventure travelling in some sort of time period appropriate. Is it too early for hot air balloons? Whatever. Isaac Newton solving crimes. Mean Machine Rex says found it. I hope they say found the docu-series I just described. But I can dream. Love Isaac Newton. Not a great guy, but you've got to put the disclaimers on it, right? Love Isaac Newton has to have a disclaimer on it as well, right? Or maybe Mean Machine Shrek says found it to mean all the primes. He's found them all. There's the sequence. We're done. It's over. I found the series on Apple TV. Good stuff. Right. I saw a review of Prime Target, which said that the main character was unpleasant, which, yeah, sounds like a crime drama. Good fun. Right, we were in the middle of a calculation, I think, because we had some matrix multiplication. That page is going to get in the way now. It's also up to the count. I added a note page about something unrelated that's calculating these convergence along the way. We need to know that. Having fun, but what do I think? So these convergence are the things. When you do matrix multiplication from the left, you are definitely doing the thing in the vary sequence with all these mediants, and adding the mediants so many times is like increasing the numerator and the denominator. That is the same thing as doing this matrix multiplication step. Yep. That's the second. What is this? That's the second. I got myself up the page. Is Pn over Q. What it remains to show that this is P over Q, which is something to do with the continued fraction. Right, working right from left. I should have stuck to my guns on the whole forwards and backwards thing, because that's turned out to be true. There's a forwards-backwards element to this. So, if we let Ri over Si be the value of the tail, the leftover stuff of the continued fraction, then we have, at the end, that's 1 over An. Why? Oh, that's just definition of what the tail is left over. Oh, maybe I should watch Quantum Leap. That's recommended in the chat. I was just catching the chat. Fable Stream recommends Quantum Leap. Definitely going to do that. Let's make a note to self. Right, good. Ri over Si is this thing. So the tail, everything you've got left over in your continued fraction, the stuff that's like, yeah, you know, like 2.5 and a bit. When I say a half, I mean some more stuff, is defined like this. So the tail would be, you've got Ai, the very next thing you're going to think about, plus all the rest of the tail. And the rest of the tail is itself a tail of the sequence. So you write it as Ri plus 1 over Si plus 1, which is then by fraction maths, this. And then P over Q, the whole thing is A0 plus this, which is an A0 upstairs. Matrices, off we go then, if we must. This is this fraction. So this fraction looks like this as a matrix. And then, what have you done here? I mean, I know what it's going to be. It's going to be the same matrices we just saw, but written the other way around. But still. Okay, so 0, 1 gives you this Si upstairs. Yeah, this checks out. Okay. And this is precisely the matrix we had before. And that very first one applies upstairs instead. It kind of is a bit different. The A0 appears upstairs instead of downstairs. Maybe I'll continue fractions to have. Can we fix this by having one more inversion? We flip the whole thing upside down? Yeah. If you do 1 over right at the start. So if your continued fraction is bigger than 1, if you just insist that your continued fractions start 1 over, that doesn't really work. It just moves the problem from all the ones smaller than 1 to all the ones larger than 1 or something. Flips the problem without solving it. Problem with numbers, some of them are smaller than 1 and some of them are larger than 1. So if you try and write them as fractions, whoa, sometimes you get improper fractions, and you cannot fix this by insisting that we write absolutely everything upside down. That just changes which one's the improper fractions. I had an idea, it was a stupid idea, but I've said it out loud on a stream now, so there we go. What am I doing? Yep, so multiplying out the big products that we had before from the right. It's got all the matrices you could ever want in there. They all look like this. Is that what they looked like before? With the OI downstairs? Bottom right? In the big products that was now 2 pages ago? Down here somewhere? Yeah, they were all down in the bottom right. That's what we had before. Okay. Okay, so we have been sort of looking at the same thing where Euclidean algorithm to calculate the quotients works from the left to give you these quotients and some leftover stuff. So I want to think about the product of a whole string of these matrices from some point to the right, or maybe some point to the left. It's matrices, the matrices that we had before. There's a small square here which I've almost got to, so let's get to that. Oh, it's almost 4 o'clock. Timing. The proof is complete. Yeah, it's convinced me it's the same product. So square at the end of the proof. So we're done. Yeah, okay. It feels like a coincidence. Don't love the proof because it just says, here's some matrices, where did these come from? And if you multiply them one way, you get one way of looking at it, and if you multiply them the other way, you get the other way of looking at it, which I don't love as a proof because my suspicion for both the streams we've done on this content so far is that I should be thinking about this entirely in terms of matrices, and then the proof is really easy because then the proof is something like, you were already thinking about this in terms of matrices. On the one hand, it's the matrices you think it is, and on the other hand, it's also the matrices you think it is. So sort of kind of want to rephrase how I think about the Euclidean algorithm in terms of matrices. I guess that's how the proof works, to sort of change what you're doing to think about it in terms of matrices instead. That's the switching step. So I'm being lazy by not thinking about it a bit more. Okay, I've noticed the next line starts an interesting fact, so I really do want to read that as well. Oh, good. Enstucky's got a question about it to challenge my understanding. Oh, hello. Do we have some guarantee that J, I plus 1, GCD, SJ are ooh. So what's the greatest common denominator of SJ? Where are you looking? RJ, AISJ. Oh, in here somewhere. Right, so I interpret that question as asking about the link between these fractions and the vectors. So that's my understanding, isn't it? I can remember that the initial fraction is in lowest common terms. And I know that when you run the Euclidean algorithm... Okay, there's a helpful fact. Let me address the question again then. Read the question again. A vector could be a multiple of the RI, SI. Oh, square brackets, J means I plus 1. That's what you're telling me. This thing in here, if you're thinking of that as a S, next one, RAIS1, which also appears up here. GCD. I think these things all have GCD1 by induction. I can't actually tell you which direction I'm doing the induction in because I've got confused. Does it matter for the comparison? Let me work that out first, I think. Well, a bit, so that if you think... So if you just keep doing the calculations without cancelling terms, then I think you get the same thing in all cases. So if you've got this, if this really is, it's not enough to conclude when you see these two fractions that Ri really is this and Si really is that. It's the ratio that's equal. I happen to suspect that both of those are in lowest common terms, because if I could prove that Ri and Si will always had GCD1, then this would be lowest terms. And reading in here, any common term between these would be a common term between these two, so therefore a common term between those two as well. So if my hypothesis that Ri and Si are always coprime holds, then I'm good. The sort of in here is the definition. Definition of the tail. So maybe I should have defined them up here when we say the value of the tail. We should probably define tail with, which is cheating a little bit. Go back to the definition. Not cheating, I suppose, but to point at the definition a little bit more. Say, hang on, when we define these just now, they haven't appeared before, but we define them just now to say that this is in lowest terms, GCD1, then kind of trivially that forces all of these things that we're talking about to, this really is in lowest terms as well. I just want to check that actually makes sense. But I feel like I've moved the problem somewhere else, so let me just reread this one more time. I'll put that in there. And then, yeah, I think that fixes it. Yeah, okay. I think we should define it, and it then follows through that you kind of do have the correct recursion relation between the Ri and literally the numerator. Maybe I need to worry about plus or minus signs. Like negative numbers feel like they've caught me out before. Is this secretly 1 over 2 on the left and minus 1 over minus 2 on the right? But probably not. I think I'd prefer this whole book if it was only about positive numbers. Brush that onto the carpet. Okay. And Stucky's letting me move on. Hello. One more. Yeah, no, I've also convinced myself, I think. Right, okay. Oh, thanks for the... What was that? Thanks for the follow. Famished edits. Thank you. Oh, wait, that counts towards this, doesn't it? That's this. I haven't had one of these for a while during the show. People normally follow when I'm not live. I think it says a lot. We're trying to get towards the smallest non-interesting number. At the moment, our follow count is interesting because it's a small number. If we get to the end of this bar, it will become not interesting, as defined by which numbers have Wikipedia pages. Small numbers over here have all got Wikipedia pages, but large numbers, some of them don't. And that's the smallest number that doesn't. Therefore, it's the smallest interesting number. That's normally presented as part of a proof that there isn't a smallest interesting number, because couldn't you create a Wikipedia page that says, isn't it interesting how it's the smallest number without a Wikipedia page? And that would be a paradox. It's interesting to note that Wikipedia solves that paradox by having a number for which the fact that it doesn't have a Wikipedia page is listed on its own Wikipedia page. Clearly false, but that's what Wikipedia have done. 314 gets all the press. 315 doesn't. Right, what are we doing? Maths, I think, but wrapping it up. Meanwhile, Famished Edits is hungry. Okay, good. Right, okay, I think we should call it there. We hit a square for a proof. Am I going to look at this interesting fact very quickly? If it's less than 1, no initial A0, reverse the numbers. What? Reverse the numbers in your continued fraction, you get something with the same denominator. That is weird. Okay, maybe this course is good. Maybe this course is good. Got it right. Sorry. I thought you were just oversharing. Good. Okay. Matrix time to prove that fact to get these two things. Oh Oh no, the number theory starts down here. Look, the product of the numerators is congruent to 1 mod the denominator. These are inverses or something. Modulo the denominator. Yeah, we've accidentally got a way to calculate inverses mod 30. They multiply to give 91. That's 1 more than multiple of 30. This is some slightly mad way to calculate. Oh no, it's the normal way. This is the normal way of calculating inverses. I've been thinking of that as Euclid numbers. Oh, okay, this is going to be good. I think this is going to be good, but I am going to call it there, I think. Time to not be live. More maths to follow. I still think this is sort of a way of packaging up things that you might already have seen, like the Euclidean algorithm, or reversing that to find Bazoo into a hyper-efficient kind of matrix way, where occasionally you look at the pictures to see what's going on the actual number line. But I'm enjoying the links, especially if it occasionally comes back to number theory at the bottom there, which is what I put in the description. Right, good. I think I'm back next week, but it does depend a little bit about whether I'm physically back at 2 o'clock next Sunday, but that's the plan. Everyone have a nice week. I might see some of you on Maths Club Thursday, of course, but otherwise, see you back for the unprofessional tea drinking one, where we do some maths. Right. This control board is different, isn't it? I need to press the stop button. Good to meet new people as well. Hi to people who've joined in this stream as well. Good to see you. Bye.